So you have there 7 bits. So 2 to the power of 7 different states, 128. And these are bit patterns, and you are now not interpreting these bit patterns as integer values like 1, 2, 3. Because if you, for example, want to write the number 10, you need the digit 1 and the digit 0. You don't need an own pattern for the value 10, because you're just using 2 bytes, 1 byte for the 1 and the second byte for the 0. And then you have the 10 if you are interpreting correctly, which means overall you just need 10 different patterns for the digits. So from 0 to 9. And you still have 118 remaining patterns, and you are using them. You can see here, for example, for symbols, for upper and lower cases. So here you have the upper cases, here you have the lower cases, and you have some additional symbols. So think on that's from 1972. And we still have the @ symbol. Where is it? It's here. Do you know why we use the @ in the mail addresses? What is the reason for using the @ there? It is because it was not used somewhere else before. So it is not used because it is symbolizing something. It is used because it was left over at that moment. So the @ was not used for something else. That's why we are dividing the receiver and the domain in a mail address with the @ If it would have been the semicolon that was not used before, then your mail address would be your first name dot last name semicolon th.de. So that's the only reason why. And you see here now the 7 bits that we have there. Bit 1 to 4 are on the left, and bit 5 to 7 are here. So you have the bit pattern 0, 0, 0, 0, 0, 0, 0, which is a null. It's not a 0. Null means nothing, empty. Or let's look on to 0, 1, 0, 1, 0, 0, 0. That's the LF. That's the so-called line feed. That's an old command from very old printers, which are similar to the typewriters, where if you printed the text such that the line was completely full, you had to feed the line to the next line to be able to print again. Okay, so you are writing a piece of text. Let me just show you. Yes, so this ASCII code is still existing. So I'm just writing anything. You don't have to. So if I'm writing here text, you see on a certain moment, my line is full and I'm starting in the next line. If you're using a typewriter, that did not happen automatically. Therefore, what you have to do is you have to move manually the paper such that you can print in the next line. That's the command there is the so-called line feed, which was used in old printers. So they got the command that they now have to feed the line. And the second command that you need for that is the carriage return, that one here, which was moving back the printing head to the original position. So really, if you printed there some text, there was the text itself that you printed, so the information, but also some control commands which were moving the printing head forward and backward, or were moving the paper in the printer such that you could print into the next line. If you are forgetting the line feed, what will happen is that you are printing the next line just over the first line on the same layer, let's say. And therefore, you need these control symbols. What else? So, in addition, interesting there is somewhere a bell here. That was really an acoustic signal. So if you send it this bell pattern, which is 1110 000 to an output device, you could hear an acoustic signal there. So like a bell. Yes. So maybe not. Do you remember when we talked about this very early stage computers, this mechanical stuff, where they had a bell for an overflow to indicate an overflow in the calculation? Something like that. So you really, and you may know still from your computers, if you're doing any input which is not possible, that sometimes you're hearing an acoustic signal which is sounding like a bell. And with old machines, this was realized by sending this bell command. And if you wanted to have the printer to print a capital W, the pattern that you had to send was 110 101. And then the machine who was printing, for example, the printer or the monitor who was displaying, interpreted that pattern as a capital W, because it was interpreting the code according to the ASCII table. So if you are using anything else, any other interpretation, then the 1110 101 is maybe a K or an at. But the standardized, this ASCII chart, is interpreting this bit pattern as a W, a capital W. And if you're now looking into the upper and lower cases, you're seeing that the first 4 bits are always identical. So for the capital or for the upper and the lower W, it is 1110, and then either 101 or 111. So the first 4 bits of the letter or of the case are the same, and just the last 3 bits are deciding if it is an upper or a lower case in this ASCII chart. So that's one way of interpreting. You can see here, so in the 1940s and 50s, many codes were designed and used in connecting with different pieces of equipment. And as always, if you have many different ways of interpreting stuff, then you're usually mixing up, and sometimes you're interpreting wrong. Yeah. No, so you have here the bit 1, 2, 3, 4, 5, 6, 7. And you remember, usually we are writing them like that. So B7, 6, 5, 4, 3, 2, 1, and 0. So it is the same way like we did up to now. So then, to elevate the situation, the American National Standard Institute, the ANSI, adopted the American Standard Code for Information Interchange, the ASCII. And this code uses patterns of lengths from 7 to represent the upper and lower case letter of English alphabet, punctuation symbols, the digits 0 to 9, and certain control information such as a line feed, a carriage return. And ASCII is extended to an 8-bit per symbol format by adding a 0 at the most significant bit in each of the 7-bit patterns, which means you have another 128-bit patterns then if you're using a leading 1 instead of a leading 0. Why? Because, for example, what you are not finding here is something like the German Ä or the Ü, you know them? Yeah. So in German we have, for example, the Ä or the Ü, also as upper and lower cases, or Ö. or in any other languages, you may have some certain cases which are not common. And therefore, the ASCII code provided 128 symbols of the English alphabet, but in addition, another 128 symbols for any other cases or whatever. The International Organization for Standardization, so the ISO, you may have heard it before, and the International Electrical Commission, the ESE, have developed a number of extensions to the ASCII, each of which were designed to accommodate a major language group. For example, one standard provides the symbols needed to express the text of most modern European languages. Included in its 128 additional patterns are symbols for the British pound and the German umlaute. So you are using 7 bits for 128 patterns, but as 1 byte is 8-bit, you have another 128 different patterns that you can adopt to any country or region-specific symbols. But then you're limited. So you do not have more than 256 symbols within one ASCII code type. And the next step into that is the so-called Unicode. That's mainly what we are using today. There are different Unicodes as well. So the most common one is, I guess, the UTF-8. And sometimes if you are using just raw text with a text editor, you have to tell the text editor how it should interpret the pattern. So is that an UTF-8 code or an UTF-16 code? Maybe you got some, or at any moment, an email with some symbols which were looking a bit cryptic. Have you ever seen, like, what I'm remembering is that you sometimes have a mail where you have a symbol somehow looking like that, so a rectangle with so like the mixture of an O and an X. And you are getting this symbol because your interpreting software is using the wrong UTF encodation. So it is, for example, not using an UTF-8 standard, but an UTF-16, but the text was written with an UTF-8 standard, and then it is not interpreting the pattern correctly. So this Unicode is a standard for the consistent encoding, representation, and handling of text expressed in most of the world's written systems, developed in conjunction with the Universal Coded Character Set, UCS standard, and published as the Unicode standard. The latest version contains a repertoire of more than 128,000 characters. So from 256 possible now up to 128,000 characters, covering 135 modern and historic scripts, as well as multiple symbol sets. The most recent version is Unicode 9, and it is maintained by the Unicode Consortium. And Unicode can be implemented in different character encodings. Usually UTF-8 or UTF-16 is used. And UTF-8 uses 1 byte for any ASCII character, all of which have the same code values like the ASCII, and up to 4 bytes for other characters. So overall, we have 5 bytes to interpret there. And the 16. So here we are using 32-bit in the UTF-16 to represent any character. And in the slides, there is a link. I just want to show it. So you can look into these videos by your own. Just 1 second. Of course, on the tablet, the links are never are usually not working. I don't know why. So you can look into the second video by your own. and after the advertisement. So what you are seeing here is the decodation of a Unicode code. So that's showing one symbol after the other, which are encoded in the Unicode. And you see the video is taking 2.5 hours. So that's just all the symbols that you have encoded within Unicode. And we see there we are at the moment at Latin, but there are even some most probably Chinese symbols. I have no any idea. For the simplest version, but if you have a 32-bit pattern, it's 2 to the power of 32. So you see there are a lot of Asian symbols. Most probably there is also somewhere some Arabic mathematical operations. So I don't know. Whenever you are not finding something interesting on Netflix, you may can look into that video, but you can do that by your own at home. So there are many, many symbols that we are able to encode using Unicode. And how we are doing that? Because we are creating a bit pattern and we just have a rule how to interpret this bit pattern. And that's now the difference between just the pure code and the real information encoded in that code. Now, yeah.
A lot of these symbols that don't read what language are they? Showing us what these symbols represent in form of hieroglyph language, like
no, that's our languages that are used all over the world, but there are other symbols as well. So, for example, especially in math, you will see if you are dealing with more complex stuff than what you are doing at the moment, there are many symbols that you may have not known up to now. And especially, is there someone who is coming from China? No. But there are, I don't know, hundreds of dialects and 100 ways of writing symbols which have a different meaning. I just saw some time ago the most complicated symbol in a Chinese dialect, I guess, is consisting of more than 40 different lines and is the symbol for a certain soup. So it's not a word like we are know. They are, so for many things, they just have one symbol, which are meaning that. And many of them, not all of them, but many of them are encoded in this Unicode standard. Now you can imagine if you are transferring this amount of bits that we have to have some error control. So you see there in communications and information processing, code is a system of rules to convert information, such as a letter, a word, a sound, image, or a gesture, into another form of representation, sometimes shortened or secret for communication through a channel or storage in a medium. So WhatsApp is advertising that now the messages that you're sending are encrypted and only the sender and the receiver can decrypt it. And this process of encoding information from a source into symbols or storage, and decoding is the reverse process. So encoding and decoding. So the decoding, please, those on the, can you please be a bit quiet? So in information theory and coding theory, with applications in computer science and telecommunications, error detection and error correction or error control are techniques that enable a reliable delivery of digital data over unreliable communication channels. So what means error detection and error correction? So if you're using an analog radio, you know that you're not getting the signal well all the time, and you're hearing some noise, but you are still able to get the information out of what you are receiving because you're doing some error correction by your own. Maybe because you're just understanding parts of it and you're able to recover fully by your own what it means, or maybe out of the context, you're knowing what it should mean. So for example, so knowing out of the context would be if I'm saying the word engaged in English, that can have two different meanings. So either you are married or you are very active into something. The real meaning you only know by the context of the word engaged. So if I'm saying he is a very engaged student, most probably I'm not talking about if he is married or not. So that is a kind of error correction. So just the word engaged is maybe an error because you don't know what it means, but out of the context, you can come back to the original meaning of the word. And the error detection is that you're realizing that there is an error. And there are some methods, even in the informatics, who are dealing with that. And many communication channels are subject to channel noise, and those errors may be introduced during transmission from the source to a receiver. So like you have with an analog data transmission, where you're hearing a noisy something, you can have that noise in a digital signal as well. And these error detection techniques allow detecting such errors, while error correction enables the reconstruction of the original data in many cases. And what we want to do now is we want to look into some examples for an error detection. So the easier part. Do you know any pattern in your daily life where you have a kind of error correction or detection at least? Sorry? Autocorrect, yes. What's a hiccup? Okay. No, I guess that's not. Is it an error correction? For your lungs, maybe yes. But you know the numbers for the bank account. So every one of you has a German bank account, right? And you got this IBAN. And this IBAN is usually consisting of DE for Germany. And then you have there the so-called Bankleitzahl, which is identifying a bank. I don't know. Whatever. And then you have some further digits and the ID of your bank account. But here you also have two additional digits, let's say 42. And this one is a kind of checksum. So maybe if you transferred once some money from the German bank account to another bank account and you typed in the wrong IBAN, it showed you that this IBAN is not correct. And it knows that this IBAN is not correct because the first two digits after the DE or 80, depending on which country you're sending the money into, are the kind of checksum. And we have such checksums in many, many places. And we will now look into a few of them. The most easiest that you can have is the so-called parity bit or check bit. And you see that's a bit added to a string of binary code that indicates whether the number of 1 bits in a string is even or odd. So if we have a bit pattern, we can either have an even or an odd number of ones there. And the parity bit checking is used occasionally to transmit an ASCII character, which have 7 bits, leaving the 8th bit as a parity bit if you want. So, and the check digit is a form of a redundancy check used for error detection and identification numbers such as International Standard Book Number, so the ISBN, you know them from the books, or the International Article Number, which are used in application where they will at least sometimes be inputted manually, and by that by an error. It is analogous to a binary parity bit used to check for errors in computer-generated data. However, this error control and error correction always costs bandwidth. That means if you have an 8-bit pattern and you want to have an error correction, then you cannot represent 2 to the power of 8 symbols, depending on how complex your error detection or correction is. If it is just a parity bit, then you can represent 2 to the power of 7 symbols, and you are using the last bit to indicate this parity bit. So how is this parity bit working? You can see it here. We have an ASCII code A on the left, which is containing an even number of ones. So we have 1 and 2 ones in this code. And now, if the pattern still, or if the pattern has an even number of ones there, we are adding an additional leading one such that the total pattern has an odd number of ones. Here we have a pattern which is still containing an odd number of ones, which means the parity bit is 0. So also the total pattern has an odd number of ones. So with this leading parity bit, we are manipulating the pattern or the pure information pattern such that we always have an odd number of ones in the overall pattern. Now, if you are sending that pattern and someone is receiving and he has a leading one, but the remaining bit pattern already has an even or an odd number of ones, then you know that you did something wrong during the transmission. So with the parity bit, you're always manipulating the pattern such that your overall pattern has an odd number of ones. If the original pattern has an even number, then you are adding a 1. If it already has an odd number, then you are adding a 0. Now, if you are transferring and what you're receiving is an additional 1 here, let's say, due to whatever reason, then you can count the number of ones in your information pattern. You have here 1, 2, 3, 4, and you know that during the transmission something went wrong, because you should have here a leading one to have in the overall pattern, again, an odd number of ones. Is that clear? So that's the most simple way that you can have for such an error control. You can detect an error, you cannot correct the error. You just know that during the transmission, there was an error. And it can only detect a single error. So if you have 2 errors, like 2 of them are getting 1, then the received pattern would again have an odd number of ones, and you would not realize that during the transmission you had an error, because it is more than a single error. And there can be even or odd parity depending on how one wants to do it. And the parity bit is then either 0 or 1, depending on how it was defined. So you can define that exactly the other way around as well. So such that the final or the total pattern has to have an even number of ones. That depends on how you are defining your communication. So if you're not using a standardized something, but you are defining by your own, then it is on you how to do that. If you are defined it like that, so it depends on. So that's something you can define by your own if you want. So if you want to realize some data transmission and you are relying on a parity bit, then you can define if the total pattern should have an odd or an even number of ones. And you are adopting the parity bit such that your requirement is fulfilled. So just for the theoretical background of this parity bit. Now we have some other possibilities of this error control or error detection, and we are using that in this international standard book number and in this EN code. And you see there, usually this international standard book number is grouped. The first one is giving you the group. Then you have the publisher. So the group is usually the country in the ESBN where the book was published. Then you have the publisher, so the company who published. You have a title for the book, and you have a check bit. So theoretically, if you have 3 numbers for the title, the publisher can publish 999 books. Yeah. So if you have an ESBN group like that, then this publisher here can publish up to 999 different books. If he wants to want more, then he has to have an additional publisher ID. And now, in addition, you have there at the end a check digit. And how is this now calculated? So we will come to the EN as well. So what you are doing here is you are multiplying the first digit with 10, the second digit with 9, the next one with 8, the next one with 7, and so on, and summing up all of these values. And then you are defining the check digit such that if you are now dividing that one by 11, the remainder is 0. Clear? So we have here 8175257660. 0. Now we have 8 times 10 is 80 plus 1 times 9 is 9 plus 7 times 8 plus 5 times 7 plus 2 times 6 plus 5 times 5 plus 4 times 7 plus 6 times 3 plus 6 times 2 plus 1 times the check digit, which is 0 in this case. And if you are summing up, that's 275. Now, 275 divided by 11 is
25.
25, right. What is the remainder? 0. So if now I would have here a 7, let's just do an example. So we would have here 14 instead, and we would have 277. What is 277 divided by 11? So the remainder is not 0. You know,
It's
you
2.
did not. Right. So you have a remainder unequal to 0. By that, you know you did not read your ESBN or input your ESBN correctly. Because the checksum or this check digit has to be such that if you are dividing the sum by 11, the remainder has to be 0. So if it is 277, the checksum has to be 9. Because then you are adding another 11. So if the ESBN would be 767, then the check digit would be 9. Because then you would add here another 9. So we would have 286, right? If you are dividing that by 11, it should be 16, something like that, right? It's 26. And again, the remainder is 0. So you are defining for this ESBN a number, and then you are having there a check digit that you are adding finally to your number. And if you are dividing it by 11, the remainder has to be 0. So this rule that the remainder has to be 0 if you are dividing by 11 is defining your check digit. So which values can the check digit have in this case? Everything between 0 and 10. Because if you are adding 10, so the lowest remainder that you can have is 1. And if you have 1 as remainder, you have to add 10, then you can divide again by 11. And how are you representing the 10 in the ESBN? You may have seen on some books. If you ever looked into the ESBN, or maybe you wrote somewhere when you referred. Because you only have 1 digit there, so you can't write the 10. It's an X. You may have seen ESBN numbers who have an X at the end. The X means the chat digit is 10. And then if you're dividing by 11 and your remainder would be 1, then your check digit is X, which means you're adding another 10, which is making your remainder 0 again. Because you can divide by 11 once more than the original number. And if you're now inputting that manually and you are dividing by 11 and your remainder is not 0, then you know that you did something wrong. So that's how you're identifying here in the ESBN, in the International Standard Book Number. Now, the second number is this, or there is a second thing. So you can do that the other way around as well. So what we did up to now was we multiplied the 8 with 10 and the 1 with 9 and so on. But you can also multiply the check digit with 10 and the very first digit with 1, and the result will be the same. So it doesn't really matter if you are reading this International Standard Book Number from left to right or right to left if you're doing the check. Why? So some math behind. Assume that we have a number with 10 figures, like our ESBN, and we are multiplying them with, or we are multiplying each of the figures with 11, right? So for sure, we can divide the result by 11. Because each digit was multiplied with 11. So, and the remainder will be 0. That's obvious. Now we can rewrite that one as 10 plus 1 times A plus 9 plus 2 times B. So we have always 11 here. So we are still multiplying all our figures with 11. Now we have the rule, which is so someone has not muted his microphone in the online group. Thank you. So there is now a following, or the following rule applies, that A plus B mod n is equal to A mod n plus B mod n, again mod n. How to understand that? Let's look into with an example. Just add a page. So the rule that we have here is A plus B mod n is equal to A mod n plus B mod n, again mod n. So let's translate that into something. So let's have 40 plus 60 mod 9. So we are dividing 40 plus 60 by 9. What will be the remainder if you are doing that? No. Right. So the remainder will be 1. So it's 11, remainder 1. So 99 plus 1. Now, the rule says that if you're dividing now, if you're calculating the modulus of 40 by 9 plus 60 mod 9, again mod 9, that should be 1 as well. So what is 40 divided by 9? right? So 4 and 60 divided by 9, 6. Mod 9 has to be 1, and 10 mod 9 is 9, is 1. So we have 9 remainder 9. So that's what the rule is saying, and you see it's true if you're doing it with that example. In both cases, we are getting the remainder 1. And that's the rule that we are applying here as well. So we can rewrite our expression like that. So 10a plus 9b plus 8c plus 7d and so on. Mod 11 plus 1a, 2b, 3c and so on. Mod 11 is 0. And that's the rule that we are applying there. As one of the expressions is always 0 by the definition, the other one must be 0 as well. So no matter if you are reading from left to right, that one has to be 0. Or if you are reading, if you are reading from right to left, that one has to be 0. By that, the other one has to be 0 as well. So that's why it doesn't matter if you are reading the just for calculating the checksum, if you are reading from left to right or from right to left. Yeah. For which one? Yes, sure, if you want. Which one? 20? Uh-huh. Right. So 10, 20 plus 30 mod 7. Would you try by your own? No, it would be 20 mod 7 plus 30 mod 7 mod 7. So you're just dividing by 7. You are not caring about the result, just about the rest. So what is 50 divided by 7? 1.
7.
So the mod is 1 here. The remainder. That's what we are calculating. And now, so what is 20 divided by 7? Or what is the rest, the remainder, if you are dividing 20 by 7? 6. And if you are dividing 30 by 7? 2. So mod 7. So you have here 1 is equal to 8. Mod 7, what is the remainder if you are dividing 7 by 8? So 1 is 1. Okay? No, the answer is that this rule is true. That's what we are proving. And by that, so if the remainder is 0, so you're in the ISBN, you're defining this check digit such that the remainder is 0. Now you can read it either from left to right or from right to left. But if the result of that formula is 0, and we know that, for example, reading from left to right is 0, then reading from right to left has also be 0. Otherwise, the overall result won't be 0. So if one of them is 0, then the other one has to be 0 as well. Otherwise, the overall resistance is not 0. But we know that it is 0 because that's how we define the check digit. And now it doesn't matter if you're applying this rule of how you're calculating the check sum, so that you're multiplying the first with 10, the second with 9, and so on. Or if you're multiplying the first with 1, the second with 2, and so on. It doesn't matter if you're doing this calculation from left to right or from right to left, because you are not dealing with the result of your calculation. You're just dealing with the fact that your check digit is such that the remainder, if you're dividing by 11, is 0. So, right, so that's one calculation. You see here we are multiplying the first digit with 1 and the last with 10. Here we are multiplying the first digit with 10 and the last with 1. You can do both ways because you are not dealing with the results of the multiplication. I mean, of course, it is not the same if you have here 80 or 8, the sum itself, but you are not dealing with the results of the multiplication. You are dealing with the remainder if you're dividing that one by 11. And there it makes no difference if you're adding from left to right or right to left. Yeah. What the mod is? Yeah. For the ESPN, it is 11. So you are dividing by 11 and the remainder has to be 0. For the EN, it is 10. That's defined. Yes? Yes? Does anyone have a book with him? Maybe? But it does not have an ESPN. No. No. So if you would talk any ESPN number and then the mod, if you're dividing by 11, so the remainder, if you're dividing by 11, is 0. That's how the check digit is defined. Clear? Then you did not read the ESPN correctly. That's how you're checking if your reading was correct or not. So for the EN, you can see the calculation on the first slide. There it is a bit differently. So you have the first digit just purely, and then the second one you're multiplying with 3. Then the next one purely, the one after multiplying with 3. So 1 times 3 times, 1 times 3 times, 1 times 3 times, 1 times 3 times, and so on. Then you are summing up, and your check digit is such, if you are dividing by 10, the result or the remainder is again 0. Because that's the definition on how this is built. So this EN, this international article number, is a standardized number that is valid or available worldwide. And it is standardized like that to calculate the check digit, you're multiplying the first one with 1, the next one with 3, then again with 1, again with 3. And yes, always. And all is for the second or for the odd digits, and 1 for the 3 for the even digits and 1 for the odd digits. Print that. Yeah.
Professor Schauer.
Yeah.
But following the ISBN.
1 second, someone is asking in the room something. 1 second, please.
Sorry.
Because the first one is the ISBN, the second one is the international article number. So the ISBN is used for books only. The international article number you are finding nearly on each product that you can buy somewhere legally. Or so if you're buying something at Amazon that has an EN. Let's do an example on this ISBN. Just 1 second. So now there was a question online as well.
Yeah, Professor Schauer, but following the ISBN pattern, are there allowed 10,000 publishers in the whole world?
No, because the group can be different as well. So the group is usually the country. Then you have a publisher. Then you have a title. So you can have 10,000 publishers per country. And if this is not enough, then you're just getting a second country code.
Thank you.
So let's look here into one book. That's just the first book I found on Amazon when I was searching for Informatics. You see, you have there an ESBN number, and you have there an ESBN 13, which is in this case the EN number. So let's maybe do that with Excel, quite easy, and I'm enlarging a bit. So that's the ISBN that we have, right? So we have here in the first one 3, 5, 2, 7, 7, 1, 7, 2, 7, 7. And we are multiplying the first one with 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And we always have here that one multiplied with that one. Then we have here, the sum. Of all these numbers. And now I have no any idea if there is a mod in Excel. Look into Excel. Yeah. So at least in the German Excel, that's called Rest. I'm dividing that number by 11. And
22.
So the remainder is 0. Okay. Now, let's say I did not copy it correctly and have here a 5. Then my remainder is 7, and I know I did a mistake in reading. So let's take any other book. Math for Informatics. So it is that ISBN. I'm replacing. So I have here 3, 5, 2, 7, 7, 1. That seems to be the publisher. Now the title is 5, 2, 0, and 7. And again, the sum is different, but the sum is different, but the remainder by the division, if I'm dividing by 11, is again 0. And you formulate 22 means that you have 20 plus 2. What do you mean by the question? What does 22 mean? Yeah, we are not caring about the result of the division. We are caring about that if we are dividing by 11, the remainder is 0. It's only about the remainder. It is not about the result of the division. The modulus operation is giving you the remainder of the division. So in German, this function is Rest, which is the remainder. If I'm dividing that number above by 11, then my remainder is 0. If I'm now changing here something, so if I'm putting here the check bit to 6, and I'm dividing that by 11, my remainder is 10, and I know that the ESBN that denoted is not correctly. Because the remainder has to be 0. That's how you have to define the check bit. So let's come back to, let's say we have here a 4 instead of. Now the remainder is 8. So I have to add 3, which would be 10 now as check bit, and the 10 is in the ESBN represented by an X. Okay? right? It's just an error detection. So this check digit is used to detect an error. For the ISBN code and for the EN code. So in the slides, you're finding a link to an article about error detection. You can read by your own, which is explaining again a bit more in detail the techniques behind and the need for it. So for the EN, as we said, we are multiplying the odd digits with 1 and the even with 3, summing up, dividing by 10, and the remainder has to be again 0. Yeah. 1. Or the positions, not the numbers. So 1 times 9 plus 3 times 7 plus 1 times 8 plus 3 times 8 plus 1 times 1 plus 3 times 7 plus 1 times 5 plus 3 times 2 plus 1 times 5 plus 3 times 7 plus 1 times 6 plus 3 times 6 plus C. 1, the next one with 3, the one after with 1, the one after with 3. So here it is just written. So you're multiplying with 1 times plus 3 times plus 1 times plus 3 times plus 1 times plus 3 times, and so on. Just the 1 times is not written on the slides. And then you are summing up again and dividing by 10. So for the check digit, can you have an X here in the EN code? Would you need an X for the check digit in the EN code? No, because the maximum that you need to add is a 9. Because you have to add a 9 if the remainder of your division without the check digit is 1. Then you are adding a 9 on the check digit. And then if you're again dividing by 10, the remainder would be 0. So the highest value for the check digit that you can have in the EN is 9. Because if you're adding 9 to 1, you have another 10. And the remainder would be 0 again. And the highest check digit that you can have in the ESBN is 10. Because if the remainder is 1 and you're adding 10, the new remainder is 0. And if you're going back now to this book stuff, let me just copy it again. So if you're looking, where is that different? So you see on the first line, the EN, on the second line, the ESBN. And the EN and the ISBN are identical beside the check digit, because the country, the publisher, and the title are the same. But for the EN, the calculation of the checksum is different. Because for the EN, you have this 1 times 3 times 1 times divided by 10. And for the ESBN, you have 10 times plus 9 times plus 8 times and so on, and dividing by 11. So therefore, the result of the division is a different one, and you have to have a different check digit for the EN and for the ISBN. Beside that, everything is the same, because the rest is defining the publisher, the country, and the title. And here you have the product group for the EN, and 978 means books in this case. So if you have a book, the EN is always 978 plus the ESBN, but the check digit is different. Because once you are dividing by 10, once you are dividing by 11. Now you have one where it is different. The EN, yeah. But it does not have an ESBN. Of course, it's not a book sold with a ESBN number, or maybe it should be. Let me just look into. Here you have the ESBN. So the 13-digit ESBN is nothing else than the EN. So that's the EN, more or less. For the soft cover, that's the same that you have printed there on the barcode. But you know that you have a 13-digit ESBN and a 10-digit ESBN, but the 13-digit ESBN is nothing else than the EN. And if you want to create now out of that 13, the 10, you have to remove the first 3 digits and adopt the check digit. Let's try. Let's say the only thing we have is now the EN, and we want to know the ESBN. Okay? So let me maybe just copy from right. So that's our calculation that we have here. Let's adopt the number. So we have 3527715,206. That's the original that we had, right? So our remainder in this calculation would be 10. But by definition, it has to be 0. So what do we have to do? We have to add to the sum 1. If you are adding to the sum 1, then the remainder would be 11, and 11 by 11 is 1, remainder 0. So instead of 6, we would to have here 7. So 3527715,207. And that's the ESBN. If you want, we can just can you tell me the EN of that one? Just the, or the 13-digit ESBN? 177 204. And that's it, right? So 173. Okay. So 177-204-8223. Yeah. So that's the EN. Now, if you want to know the ESBN, we can add that here, 77-204-8223. So our remainder is 10. So we have to add one more. So 4. Now our remainder is 0. So the ESBN of that book has to be 177-20-48-224. It's an Indian book, right? Is there Amazon in India? Is there an Amazon.in? Or okay. Let me just finalize that, please. Right. It has to be that value where the remainder is getting 0. That's not the book that you have there, right? Or is it? It is that. Okay. Yeah. So now I only searched for the ESBN, not for the EN. And I got that book. Because we calculated the ESBN by our own. Clear? So, and the check digit is always such. So you have to choose the check digit such that for the ESBN, the remainder, if you're dividing by 11, is 0. And for the EN, if you're dividing by 10, is 0. And that's why you have a different check digit for EN and ESBN. Because once you're dividing by 11, once you're dividing by 10.
In this case as well, the publisher, there's only a limited amount of publishers you could have per country.
If you want to have more, then you have to have another country code. Yeah. But theoretically it is, yes. Yeah. Yes, I mean, in addition, it is like that. If you are publishing a certain book in Germany and Austria, let's now say, because both are German, or both countries are speaking German, you are not getting a different ESBN in Germany and Austria. So that's a unique identifier, a global identifier. So now, once we know this EN, what you see immediately there is that there is a barcode. So usually, you know, if you're going to a supermarket and you are buying something, what you are buying has a barcode and an EN code as well. It does not have an ESBN if you're buying a yogurt, but the yogurt has an EN. And this EN is not typed in manually. It is read with a barcode scanner. Because what you have here in the barcode is nothing else than the coding of the digits written below. So with these lines, you see they have different width, and you have theoretically a white line and a black line, and these lines are encoding some digits. How are they doing that? So the EN13 barcode, based upon the UPC-A standard, was implemented by the International Article Numbering Association in Europe, and EN is a superset of UPC-A and used worldwide for marketing products, often sold at retail point of sale. The only difference between EN13 and UPC-A is the number system code. In UPC-A is a single digit from 0 through 9, whereas in EN consists of 2 digits ranging from 00 to 99. So which doesn't really matter if you're representing a 13 as 13 or as 1, 3. If you are reading, for you, it's both 13. So that's the only difference. And then the EN character is represented in 7 elements consisting of 2 bars and 2 spaces. No bar or space may be longer than 4 elements, and the only exception to this rule is the left and right guard bars and the center guard with 3 or 5 elements. We will immediately look into. And all characters in the left-hand side of the bar code always start with a 0, while the characters in the right-hand bar always start with a 1. So if we are looking into here, what we have here, and then we are doing the break, we have the left identifier, the right identifier, and the middle identifier. And after the left identifier, we are always starting with a 0. So this white line here means 0. And after the middle identifier, we are always starting with a 1, which is this black line. So what you have here is 0, 1, 1, 1, 0, 1, 1. That's what's encoded in these lines. So, and the width of that line is telling you if it is 1, 1, 1, 1, 1, 1. We will do after the break much more in detail. So there are some slides on that. Yeah. Sorry? you only have a check digit for the whole number, for the whole code, not for a part of that. For the EN, if you want to find the check digit for the EN, you are multiplying the first digit with 1, the second with 3, the third with 1, the fourth with 3, the fifth with 1, the sixth with 3. And then you are summing up and dividing by 10. And the check digit have to be such that the check digit is, you have to set the check digit such that if you are dividing the sum according to that rule by 10, the remainder has to be 0. No, C is always times 1, because 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And we said we are multiplying the odd positions with 1 and the even positions with 3. So 13 is an odd position, so we are multiplying with 1. Right? Because it is an odd position. So 1 times, so you are adding finally 1 times the check digit. And if you are, and the check digit has to be such that if you are dividing by 10, the remainder is 0. So if the result would be 12.3, then the remainder would be 30, no, whatever. No, but that's explained on that slides, that it is no difference. You can try to read through again, because there is a rule why it doesn't matter for the ESBN, not for the EN, if you are reading from left to right or right to left. Sorry there? So the highest number for the check digit in the ESBN is 10. The highest number for the check digit in the EN is 9. Because then the remainder is always 1. If you're adding 9 and dividing by 10, it's 0. If you have remainder 1 and you are adding 10 and dividing by 11, you have again a remainder of 0. Okay. So let's continue in 15 minutes after the break.
Hmm.
So maybe just as a short review of this EN and ESBN stuff. So the divider for the ESBN is always 11. That's a fixed something. So that's how it is described. And the divider for the EN is always 10. So you don't have to divide by 9 or by anything else. If you want to calculate the check digit for the EN, then you have to divide by 10. That's the rule. And now we are coming to how we can read these barcodes. And you see there are two groups of numbers plus one in front. If you are looking into the EN, so we have one group of numbers and we have the second group of number and we have one number in the front. They are encoded in the barcode. So these numbers are written here within that code, so such that they can be read by a barcode reader. And that consists of 95 lines. So now if you would count them, you would not be able to count, because if you have a thicker line, that does not mean that's a thicker line, that's just 2 or 3 lines in parallel. So like a 1, 1, 1. So
How big are exactly the lines?
how? The length is not so important. So it's the the widthness of them. And usually there is a ratio on how this code has to be printed on a product. So that cannot be any ratio. There is a fixed something how you have to print that on your product, especially the width of the overall code. So on the left and right side, there are 3 bit markers. That's that one here. That's the left bit marker and the right bit marker. These are those who are longer. And there is a 5-bit marker in the middle. So here you do not have black, white, black. Here you have white, black, white, black, white. Okay, 5 lines. You're just not seeing the white one that good. Which means we have 84 lines which are over. So 5 plus 3 plus 3 is 11, and 95 minus 11 is 84. To encode the figures, and now we are encoding here 12 figures, or which is allowing us to encode 12 figures with 7 lines or 7 bits each. Why do we have now? So what we need to encode are just 10 different digits. So from 0 to 9. And therefore, how many bits would we need theoretically for 10 different digits? 4. 2 to the power of 4 is 16. 2 to the power of 3 is 8. So theoretically, we would need 4 digits only to encode the values from 0 to 9. So 4 bits would be enough, but we have 7 bits. Why do we have that? Because there is some redundancy in the system. And each figure is now represented by 3 different codes. So it is not just 0, 0, 0, 1, 1, 0, 1, 1, means 1, 2, 3, 4. But we have 3 different ways we have 3 different patterns for a 0. We have 3 different patterns for a 1. We have 3 different patterns for a 2, and so on. So overall, we have 10 times 3, so 30 different patterns. Because we are representing each number with 3 different patterns. And we will immediately see why we are doing that. It is done to, first of all, clearly identify the direction when scanning. So are you scanning from left to right or right to left? You don't know. So if I have the product on top, then I don't know that I'm scanning in the wrong direction, first of all. I'm just seeing white and black lines. So I do not know by heart if I'm reading from left to right or from right to left. But if I'm encoding the left and the right part of this barcode with different codes, then I can see if this is the left or the right side, because the patterns are different. So if I'm reading there a pattern which only can occur in the right side, then I know I read it from right to left. And the rules for encoding the left figures differed from the right figures. And now let's look on the tables, which are explaining that a bit. So here you see we have the figures, the 10 figures, so from 0 to 9. And we have a so-called L code, a G code, and an R code. Why I use that color, we will see immediately. So the R code and the G code are just mirrored. You see, and the L code is an inverted R code. So we have 0, 0, 0, 1, 1, 0, 1. And for the R code, we have 1, 1, 1, 0, 0, 1, 0. And all figures on the left side are encoded via the L or R code. So in our left part of the QR code, that one we are always using either an L code or an R code, a G code, an L code or a G code. And in the right side, we are always using an R code. So left L code, right R code, and in addition, the G code. And now, which code we are using is defined in the first digit. So in this case, the digit that we have is 9. 9 means we are using LGGL. So that means the 7 is written with L code, the 8 and 8 are written with G code, the 1 is written in L code, and then GL. The 7 is G, and the 5 is L. And this 257665 is R code. So if I'm now seeing here an R code first, then I know I read that part firstly. If I'm seeing an L or a G code, then I know I read that one firstly. And how I have to decode is described in the leading number. So if it is a 9, that means it is LGGLGL. If it is 0, it is just L. If it is 4, it is LGLLGG. Yeah. Sorry, how? So we know that the red part is always an R code. The right part. The left code is always L and or G code. Always. So that part is always coded with an L or a G code. And each digit can be either L or G. So it is not always L or always G, it is a mixture. And how the mixture is looking like, so the recipe for the mixture is encoded in the first digit, according to that table. So here we have a 9 in the first digit, which means it is LGGL. But on the right side, it is always an R code. Okay. Now, here you are seeing now the codes, how they are looking optically. So a 1 as L code is 0001101. So you have here a 0001101. That's the 1. Then if you're looking for a 1 in the R code, that's 1110010. And it is looking like that, 1110010. Yeah.
Case the L code and R code, the left side and the right side have their own separate kind of code.
Right. So the right side, that one here, is always a R code. That one here is always a L and G code. And if now the 7 is L or G, is defined by this leading 9, the leading 9 says it is L. So you see, we have here 0, 0, 1, 1, 0, 1, right? 0, 0, 0, 1, 1, 0, 1. So we have here 0, 0, 1, 1, 1, 0, 1. So the first digit is defining the sequence for the left part, L and G. The right part is always encoded with the R. And then you are reading these patterns, and by that defining how you have to interpret the pattern. So that's just white and black. That's not an information, first of all. It's just white and black, and you know that one line has a certain width. And if you are now interpreting that as 1, 2, or 3 lines nearby, depends on the width. And then you are creating out of that zeros and ones. But how to interpret the zeros and ones depends on if you're on the left or on the right. If they're on the right, then you use the R code. If they are on the left, then you're either using the L or the G code. And how on the left you have to set up the code is defined by the first digit. So the first digit you have to read directly. Yeah. That's only for EN now. The barcode is only for EN. So there is no barcode for ISBN, only for EN. Yeah.
Question: why do we actually need code? Because L code is just the inverse in the inverse way.
Yes.
Way of the R code. Why do we need G code exactly? The left side.
That has something to do with the so-called Hamming distance. The Hamming distance. That's what we will come to in the next step. So as we told, theoretically, the only thing we need there are 4 bits to encode these patterns there that we have to have for these 10 different figures. Now we have more patterns available because we have 7 bits, so we have 2 to the power of 7, which is 3. 128 different patterns that we can create with the 7-bit. Okay, and now we are coming into something called the Hamming distance, and with the Hamming distance we can do some error correction, but we will see after how this is working. So up to now we always only changed 1 bit. So we had, for example, 0, 0, and in the next line 0, 1, and we only changed 1 bit. Then we had 1, 1, and we again only changed 1, 0. There we changed 2 bit, then 1, 1. And with this Hamming distance, or if you have a Hamming distance of 3, then you have a systematic which is guaranteeing that between each valid pattern at least 3 bits are different. And by that you can make sure that you are not reading the code wrongly, especially in that case where you are reading something manually, let's say. So we will come to that later, but just to explain a bit. So let's say you have a 1, 1, 1, which is an 8 in decimal if you're interpreting that, and you have 1, 1, 0, which is the 7. So now there is only 1 bit changing. So they are just differing in one state. Now, if you are transferring that due to any interferences, it can be that you are making out of that a 1. And you would interpret it as 8. You would not realize that there was a mistake. But if you may now interpreting the 8 as 0, 0, 0, and the 7 as 1, 1, 1, and for 6 you would use something completely different, if you are now transmitting instead of 1, 1, 1, 1, 1, 0, you know that's not 7 and nor 8. So there is an error. And with this Hamming distance, you can also do an error correction. So, but we will see in the slides a bit more, then it's a bit easier to understand, because you can now say the Hamming distance between, so let's say before you transmitted a 1, 1, 1 and then a 0, 0, 0. And now the Hamming distance here is 1, because just 1 bit changed. Here the Hamming distance is 2, because 2 bits are changing. And then you're saying, most probably that was not a 1, 1, 0 nor a 0, 0, 0. It was a 1, 1, 1 because I had 1 error. So with that, you can do a kind of error correction, not just error detection with this Hamming distance. And what we have here, so we have here 7 bits. With the 7 bits, theoretically, we can decode 128 different figures. We are using that to encode 10 different figures in 3 different ways, so 30 overall. So we have still 92 remaining. So, oh no, 98 remaining. So we can now choose this pattern such that they are differing. And if you are now reading a pattern which is not defined due to any error, let's say you have this barcode on a newspaper and it is getting wet and someone is scratching over, then this barcode is damaged. But nevertheless, you can read it. Because you know the 1, 1, 0 is not existing. It's only a 0, 0, 0 and a 1, 1, 1 existing. So it has to be something in between. What is the most famous thing that all of you for sure used regarding this error correction? With such a code, a barcode, a QR code. So you know the QR codes that you are reading with your phone and then they are somehow ending up in a link, let's say. Very often in the middle, they have a company sign. Usually that's an error in that code. But the error correction of this QR code is so good that it is allowing you to have that error in the middle, to have there a company sign. So it is not previewed, that company sign. There is no space previewed in the middle of the QR code where you can have a company sign. It is just like that the error correction of this QR code is so good that you can place there a company sign, for example. So let's see. With that one, I most probably am logged in. So you know this WhatsApp web, most probably, and you have there a QR code, and in the middle you have the WhatsApp sign. Okay, so that's an error. That's like a damaged barcode where someone scratched something away. But the error handling is so good in this QR code that it is able to deal with that. Because the bits are described such that you can do an error correction. So what you have there is also nothing else than a 0 and a 1. You're just interpreting. There is a way, I don't know, I have no any idea how it is exactly in the QR code. Maybe you have there 2 figures in one line, let's say. I don't know, or 3 figures in one line, or maybe. And you are creating their different bit patterns, but you are not using, so maybe coming back to that. Let's say we have this table with the 3 bits. Maybe I have to do that on the whiteboard, on the slides. Otherwise, those who are online are not seeing. So let's say we have a table, or we have 3 different bits, so 8 different patterns. Now, theoretically, I can encode with that one 8 different figures, right? But I'm deciding just to encode with that one 3 different symbols or figures. And if I'm reading now, for example, a 001, I know for sure that's wrong, because that pattern is not defined. Thank you. So I having a kind of overhead there, because theoretically for 3 figures, 2 bits would be enough. But I'm spending an additional bit to allow a kind of error correction, so of having this Hamming distance. But we will come to this Hamming distance a bit later. So here we are using 7 bits to represent just 30 different figures, which are overall just 10 different figures. But for each figure, we have 3 different codes. And how we are integrating that, so that's now the knowledge you have to integrate the data correctly, is described, first of all, by the position, left or right part of the barcode, and by the leading number, which is telling you how you have to apply the L and G code to the left part. Now, the advantage there is if you are reading that. So you are reading here the scan, so 4003994155486. And you are doing 2 scans with your barcode reader. In the first scan, you are reading from here to here. So you're reading just that part. Where is my laser pointer? So from here to somewhere here. So you're reading the 0039 in the first scan. In the second scan, you are reading the rest. So 994155548. And now we're interpreting that code. You know the 4. So the 4 tells you it's LGLLGG. And you know, here you have the separator. So you have from there on the LG code. And here you, wait, sorry. And here you have to apply the R code. And now you're looking into, so the first pattern that you are seeing here is 1100110. In R, 1100110 is a 1. So what do we have here? A 1. And we know that we have to use the red table because it's the right side, it's the R code. Because the 110011, you are not finding anywhere else here. So here you always have a leading 0. So if you have, here you always have a leading 1. So if the code is starting with a leading 1, for sure, it's R code. If it is starting with a leading 0, for sure, it is L or G code. And then you have to look into, so let's look, for example, here. So here we have 0001101, I guess. 0001101. So that's L code 0001101.